Hello everyone, good morning, good afternoon, good evening. Thank you so much for joining us today. My name is Caroline Maître and I will be your webinar host coming to you from Bordeaux, France. Today's the race is on optimizing EE systems development to capture eVTOL market share. I am delighted to welcome as our speaker today Mr. Anthony Nicoli. So Anthony leads the aerospace business for Siemens Integrated Electrical Systems segment. He is charged with expanding IES contribution to this market. Prior to this role, he led the Mentor Graphics technical sales team serving the Boeing company. He spent nearly 20 years in the defense industry, developing electro-optic and electro-acoustic systems and businesses, working primarily in the tactical missiles, countermeasure, and underwater imaging domains. So thank you, Anthony, for being with us today. I will now make you presenter so you can start this presentation.
Welcome to this webinar on EE systems development for eVTOL platforms. For those of you who don't know, eVTOL stands for Electric Vertical Takeoff and Landing. Now, I know most of you already know that, but it's always good practice to define your acronyms. The eVTOL market is hot right now. Where a few years ago, many doubted whether this segment would be viable, today companies like Vertical Aerospace, Eve, and Archer Aviation have secured orders for billions of dollars worth of aircraft. Others, like Volocopter, are getting their first regulatory agency approvals for production. But we're not out of the woods yet. Several authors have cited, in any new industry, the challenges to success are often far greater than the picture painted by optimistic new company founders. As these startups pursue public offerings, project completions, and entry into service, they will face increasing pressure to satisfy shareholders. The eVTOL segment is emerging against a backdrop of change in the aerospace and defense industry. It's putting the industry to the test generally. Pressure to meet and preferably beat program cost and schedule targets is perennial. In addition, customers expect that modern platforms satisfy the demands of increasingly complex missions. That of the urban air taxi is one of these. Commercial, business, and defense customers are demanding innovative capabilities more frequently, on a reliable schedule, and at a cost they can afford. Consequently, aerospace and defense platform OEMs are turning to new approaches to add the capabilities needed to satisfy these missions. These include a global network of suppliers and increased platform electrification. What do I mean by increased electrification? Well, the capabilities required of a modern aircraft can often be better supplied and sometimes must be supplied by electrical and electronic systems. This has led to a platform systems concept known as the more electric aircraft. For example, hybrid electrohydraulic actuation systems are not only lighter weight, they are more reliable. Capabilities like all-weather synthetic vision are necessarily provided by multiple electronic systems working together. And while this has added some miraculous things to our aircraft, it has also increased complexity. Complexity during development, platform integration, and certification. Taken together, these trends have escalated program risk in a way that has seen the aerospace industry struggle with ever-increasing program costs and schedules and embarrassing overruns. Turning to the eVTOL segment in particular, its challenges are similar but more acute. To start, this segment is primarily made up of companies funded by external investors. Reliance on investor funding means that hitting program milestones is more critical than ever. A missed milestone at the wrong time can put the company's viability at risk, or worse, force founders to cede control in order to stay alive. Program progress must be achieved despite significant technical unknowns. The eVTOL industry's first prototypes are developed. Next, eVTOL aircraft aren't just more electric, they are all electric. Their inclusion of electrical propulsion adds a new layer to electrical and electronic system complexity. At the same time, this stresses performance margins due to battery limitations. Third, the acceptable certification procedures are still being defined and are evolving rapidly. Currently, no vehicles have received type certification, although many projects are in the works. Finally, achieving production profitability will be essential to these emerging organizations. As many will outsource substantial portions of the aircraft, subcontractors will need to quickly receive and act on evolving manufacturing information. Manual interpretation and data transfer will be an obstacle, as they are costly, time-consuming, and prone to error. So, what are the implications of these trends for these companies? Let's dig a little deeper into each one. There are currently hundreds of companies trying to develop electric urban air mobility vehicles in order to provide air taxi services. The first few to reach production will win. Many of these companies are startups, relying on investor funding. Large OEMs have also invested in the eVTOL market. They have established partnerships with these startup companies. Regardless of funding source, though, it is imperative that these companies demonstrate progress and minimize issues to retain investor and partner confidence. Intense competition exists between teams pursuing the urban air mobility market. Investors and OEMs will back the strong companies, those with a robust plan and a demonstrated ability to execute. Missing one significant milestone undermines confidence and could put an eVTOL company out of business. eVTOL is a new type of aircraft. There are many risks to stakeholders as the technical unknowns associated with their mission are discovered and addressed in the development of the first prototypes. Let's take a closer look at the urban air mobility mission. Fundamentally, the goal is to provide faster urban transit, priced like a taxi. What does this mean? Well, in New York City, it takes a taxi between 40 and 75 minutes to travel from downtown Manhattan to JFK. This costs anywhere from $80 to $100. The air taxi's mission is to cut this travel time to 7 minutes, while charging roughly the same price. This is 5 to 10 times faster, and if you've ever traveled to or from a New York airport, you know this is desirable. This was tried by airlines operating helicopters years ago, but they never achieved cost competitiveness. Today, their operating costs still make a flight like this run around $200. eVTOL aircraft are expected to realize gains in efficiency, reliability, and maintenance that should turn into inherent operating cost advantages. They are also expected to be priced at half the cost of a small turbine helicopter. If they can achieve these things, it would make them initially cost competitive with ground transport in high-value markets, and later, after running down the production learning curve, competitive with taxis generally. Now let's take a look at a typical eVTOL platform development program. It's easy to make some general conclusions right away. First, it's a long time between aircraft concept and initial production delivery and revenue. While on average it takes 7 years, it's not unreasonable to expect a single iteration in any stage to extend this to a decade. Second, it's a costly endeavor, running between $800 million and $1 billion to get to first delivery. When you think of the performance that the platform must deliver, in the context of the many milestones shown here, you can start to appreciate the pressure even one development hiccup can place on these teams. Now let's get back to the fact that eVTOL aircraft are all electric. eVTOL aircraft rely on electrical power for propulsion, adding a new layer of difficulty over traditional aircraft. They also have a high level of electrical, electronic, software, and communications network content. Together, these result in an EE system of high complexity. At the same time, performance margins are thin due to battery limitations. Battery energy density is low compared to jet fuel and is not increasing fast enough. The startup nature of these companies means that they are working in a fast-paced environment with a lot of change. It can be difficult to manage the complexity of the systems involved. This may lead to many additional iterative cycles of design, test, correct, and retest. This complexity, coupled with energy density limitations, poses a significant risk to meeting performance requirements, including travel range. Here's a sampling of the EE systems used on eVTOL aircraft. Note that they employ everything from sophisticated power generation, power distribution, and motor control, to advanced display, vision, communication, and navigation systems. The most capable include autonomous flight control. These systems are connected using advanced avionic networks to facilitate intercommunication, while minimizing both the extent and the weight of the interconnect wiring required. Integrating systems like these has traditionally been done using manual approaches that employ a collection of disconnected tools and rely on the attention and accuracy of tens to hundreds of subject matter experts. In the past, aircraft programs have been able to avoid major problems because EE systems were less pervasive, and therefore there was a lower probability of EE systems problems arising. With fewer EE integration problems to tackle, prototyping and lab testing could be used cost-effectively to identify and resolve these problems. But no longer. With the increase in EE system content and complexity in modern platforms, manual approaches are undermined by human error, and integration issues can multiply. Traditional prototyping and lab testing is overwhelmed in multiple expensive iterations of design, build, test, and fix. The likelihood that a major problem will manifest as a significant program issue has increased significantly. Now let's turn to the issues of electrical energy storage. In recent months, I've seen more and more articles like this one, claiming that the commercial viability of an eVTOL platform can hinge on the type of battery used. Why is that? When compared to liquid fuels, the energy density of batteries used in today's electric vehicles remains low. You can see here that liquid fuel enjoys a 50-to-1 weight advantage and a 13-to-1 size advantage. Furthermore, unlike liquid fuel, batteries don't get lighter as their energy is consumed. This means that eVTOL aircraft are often limited to shorter travel distances and briefer flight times. This makes selecting a battery with the right, usually highest, energy density essential to commercial viability. But just as important is optimizing the platform's EE system and the infrastructure that supports it. Minimizing EE system power consumption and reducing the weight associated with fixturing, wiring, and cooling, together with battery selection, can mean the difference between an interesting concept aircraft and a commercial success. Next, let's consider the challenges associated with eVTOL type certification. Currently, no vehicles have received certification, although many projects are underway. The certification environment for eVTOL platforms is currently being defined. It is evolving rapidly. For example, the FAA has only recently published a proposed concept of operations for urban air mobility. The regulatory agencies are also working through certification details unique to eVTOL, such as electrically powered vertical lift. New design and certification guidelines are appearing well into existing development programs. Furthermore, these initial type certification events come at a time when the regulatory agencies are paying much closer attention to the details of each OEM certification process. They are increasingly enforcing the more stringent regulations associated with aircraft EE systems, including the more stringent EWIS regulations. Waivers and exceptions are hard to come by. Anyone seeking to certify an eVTOL aircraft needs to be able to respond to these changes quickly, generating and reporting supporting compliance evidence in a way that allows the regulatory representatives to rapidly assimilate it for compliance determination. Data management and design control are essential. Unfortunately, current compliance analysis and certification methods were also developed in the era of simple EE systems. They handle data in a fragmented way, with it being held in multiple drawings, documents, spreadsheets, and databases. They also use multiple disconnected, often very old tools. Many of these are bespoke internal tools written years ago in Fortran. To conduct the necessary verification, checks, and analyses, data must be re-entered manually many times. Then their results must be massaged into reporting formats that can be consumed by the relevant DERs or ARs. It's not that we can't demonstrate compliance with today's approaches. It's that they are onerous, slow, and expensive. We can't afford to perform the bulk of the required analyses and checks more than once. It can take weeks to report on the impact of a single design change. So when a compliance analysis iteration arises, whether from a desired design improvement or from a changed regulation, it blows our schedule and cost budgets. We checked with engineering teams charged with this work, and here's a sample of what they reported. One person said, "I never know if I'm analyzing the current data." Another reported, "There are a lot of findings in peer review due to errors." Yet another one said that sometimes we forget to analyze entire buses. And finally, one said that we spend weeks writing the report only to find that the references are outdated. With multiple compliance analysis and reporting iterations expected as regulations for eVTOL aircraft change and evolve, current methods add risk to our ability to achieve type certification in time to be a viable player in this market. Finally, let's turn to manufacturing. Companies entering this market are focused on innovative solutions and time to market. Many of them are not planning to set up their own manufacturing facilities, but rather will subcontract the work. Ideally, they could release mature, stable designs, production data, and orders to their contract manufacturers, who could in turn then invest in production tooling and factory upgrades that they could use for the duration of the production run. Unfortunately, this is unlikely, as change in aircraft design, including the EE system, is expected to be the rule rather than the exception. The most fundamental drivers of this change will arise from discoveries during detailed design, prototyping, and initial flight test. Some will be opportunities to improve market position. Others will be necessary to address late-breaking problems found in integration and test. Addressing many of these will not be optional. They will result in new production data packages delivered to subcontractors. Responding to certification issues is the second fundamental driver of these changes. Here, eVTOL OEMs will need to respond to the changing regulatory environment and address compliance shortfalls found during their test and approval cycle. Again, most of these will not be optional, and many will result in design and production data changes that will impact subcontractors. Recall that achieving production profitability will be essential to these emerging organizations. Both the eVTOL OEMs and their subcontractors must respond urgently, as EE system and EWIS changes are frequently communicated at the last minute, with little time to respond if a production program is to meet its schedule. Data management, design control, and rapid, traceable production package creation are crucial when companies are subcontracting. Manual interpretation and data transfer will be an obstacle, as they are costly, time-consuming, and prone to error. Those OEMs who build partnerships and practical digital communication channels with their suppliers will minimize the struggle to respond to these changes. The most advanced will turn responding to change into a source of competitive advantage. Companies competing for the eVTOL market cannot afford to get tripped up by the challenges and risks I've outlined. Excellence in executing all these aspects of the platform and corporate lifecycle is essential for company viability, as market acceptance of these new aircraft is not guaranteed. To minimize these risks, forward-thinking eVTOL companies are following in the footsteps of other OEMs and adopting a model-based EE systems development approach. So how can eVTOL companies respond and be successful? So, just what are the characteristics of a successful EE systems development solution? First, successful EE systems development solutions leverage the digital twin to identify and prevent errors, analyze performance, and quickly complete trade studies. This reduces risk early in the design, resulting in reduced cycles of trial and error. Second, they employ design tools that have strong multidisciplinary integration. This allows development experts from various electrical and mechanical implementation disciplines to collaborate in real time and as the program progresses. It accelerates the design process and eliminates integration errors from the start. Third, they connect the certification and design teams through a digital thread. This allows certification analysis and reporting to be derived directly from a configuration-controlled digital twin of the EE system, no longer subject to the delays, errors, and confusion that arise from manual data communication. It also provides digital traceability to design and requirements data. Finally, they use the same configuration-controlled digital twin to automatically derive the manufacturing data necessary for both internal and external production groups. This provides a rich set of production data to specify tooling and program advanced manufacturing tools, accelerating a production team's response to inevitable change. Siemens Digital Industries has developed an integrated software portfolio that exhibits these characteristics. Known as Xcelerator, it is multidisciplinary, providing lifecycle solutions in the mechanical, electrical, and software domains. It employs a flexible, open ecosystem, allowing IT systems to work well together. Capital is the EE Systems Development Suite within the Xcelerator portfolio. Capital was conceived and constructed as an integrated environment for end-to-end model-based EE systems development. It employed a digital twin, or a representation of the EE system as a digital data model, long before this term became popular in the industry. By leveraging digital data continuity throughout the development lifecycle, that is, by using a comprehensive digital thread, Capital sources necessary inputs from sister disciplines and connects this model with program stages that require its information. Capital automates the creation of the EE system's digital production and utilization twins. It uses generative algorithms to derive these directly from the released version of the EE system. Capital is comprised of three major blocks: systems and architecture, software and networks, and electrical and harness. These enable model-based EE system architecture development, including optimal allocation of hardware and software functions. They also transform these system models into end-to-end optimized electrical, electronic, network, and software outcomes. Upstream, they link to platform-level requirements and multi-domain system models, ensuring that the EE architect remains aligned to the overall system requirements and constraints. Downstream, they provide executable EE system descriptions for overall system verification and validation. At each level of the EE system hierarchy, Capital helps those responsible for architecture design and integration understand what's expected of them, explore and optimize architectural possibilities before releasing development direction, share design intent with the EE implementation teams, and determine if the implementation team has contributed what is needed. Capital includes a complete flow for electrical wiring interconnect system development. This includes EWIS design and analysis, harness design and manufacturing engineering, compliance analysis, tooling, that is, form board design, manufacturing data prep, work instruction generation, publications generation, and maintenance support. It also includes a complete avionic networks design and verification flow. Both flows exploit Capital's digital twin and digital thread to enable automated, correct-by-construction generative development. The environment also includes domain-specific data and process management, while being natively integrated to the Xcelerator PLC data backbone. It enables EE system implementation in the context of the platform's physical environment through mechanical co-design. Rather than continue to tell you about it, let's take 2 minutes and watch it in action. You can see that Capital delivers on what I've been describing. I'd now like to share with you a few of our customers that have adopted Capital and are enjoying the benefits of model-based EE systems development. This slide shows 3 helicopter OEMs, Boeing, KAI, and Bell, and 1 e-aircraft maker, By Aerospace, who have all adopted Capital. Don't worry, we have eVTOL companies in our customer stable as well, but the segment is so competitive, none would consent to share their names. Perhaps Bai's experience is the most relevant to this audience. In a recent presentation at the 2020 Siemens Realize Live event, Jim Forrester, head of Bai's engineering team, made the following comments. Capital is designing the first all-electric certified aircraft. He was referring to the Bai E-Flyer. The Capital NX integration is very good. Capital is being used out of the box. We decided to just make their processes ours. The team tried to do this in other tools and were unsuccessful. But with only 2 days of training in Capital, they were able to do it. Capital exceeded our expectations. And if you look carefully on this slide, you'll see the primary value they are deriving from Capital. It is very germane to the eVTOL challenge. They are using Capital to perform integrated mechanical and electrical design to optimize the E-Flyer's EE system for weight and power. And that concludes my presentation for today. I thank you for attending, and I invite you to participate in the ecology of industry leaders who have adopted Capital and model-based EE system development.
With that, I would like to thank again our expert and I would like to thank again our speaker and expert today, so Mr. Anthony Nicoli. And thank you all for joining and for your interest in Siemens Global webinars. The session is now closed. Goodbye.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.